Hello students, this is lecture number 38 and we are into the last chapter, not last chapter in your book. There is 11th chapter as well, which is about the like abacus simulation and all. So, but as far as this course is concerned, this is chapter 10 is the last one. So, and we have some idea about the chapter 11 already before the midterm exam. So, this chapter is about beam, right. So, this is beam bending, right, and we already derived the Euler-Bernoulli beam equation, and which looks like this, which is d square dx square ei d square uy over dx square minus px equal to 0, and subject to some boundary conditions, and boundary conditions are on. So, there are, you can say there are some boundaries, let us call it gamma u, where this is given, what is given, uy is given. So, uy equal to uy dash, which is given, let us say. Then there is a boundary, let us call this is gamma theta, where theta equal to duy over dx equal to theta bar is given. Then let us say there is some boundary where m is given. So, this is m is given. So, where m means ei d square uy over dx square, okay. So, equal to m naught, which is given. Then there is a gamma v, where the shear force is given, and that means which is d over dx ei d square uy over dx square, yeah, and which is equal to v naught. So, these are, you can say there are 4 types of boundaries, okay. So, here the boundary actually meaning that there are like 4 kinds of boundary conditions, okay. So, the condition over the displacement, and then the slope itself, then on the bending moment at the ends, or the shear forces at the end. Yeah. So, these are the 4 possibilities, and a combination of that are typically you see in a problem. Okay, now next thing is we will use these to actually find out the weak form. Yeah. So, weak formulation. Okay. So, weak formulation we can use the short one also. So, let us use from this the original one, which looks like d square m over dx square minus p x equal to 0. So, we will just use this one, and we know that m is where m equal to ei d square uy over dx square. So, that we will put later on. Okay. So, for the time being, let us start from here, and the weak formulation will be we have some w, which we multiplied with this, and we have d square m dx square minus px, yeah, and then we have dx. It goes from 0 to L because this is a beam something like this one, right. So, here we have x, this is x equal to 0. So, this one becomes equal to 0. So, or so now what we are going to do, we will do integration by parts. So, same as earlier, okay. So, we will do some the integration by parts. So, we can first we will do separate it. So, 0 to L w d square m dx square dx minus 0 to L px w dx equal to 0. Yeah, okay, okay. Or here integration by parts we will use. So, we can use do like this 0 to L w d over dx m over sorry, just m, yeah, d m over dx like this times dx minus 0 to L w px dx equal to 0. So, from here we will get idea, right. So, that means this will just get out. So, we will have w times dm over dx. So, you can see this one as this only, this dx and dx will get cancelled. So, you have d of dm over dx. So, we get w times dm over dx minus then dm over dx we get here, and then we get d dw over dx. Yeah. So, so what do we get? So, or and we get w. So, here integration by parts. So, w times dm over dx. So, w times dm over dx from we have at L to 0, okay, minus and minus will get dw. So, here we get dw over dx times dm over dx. Yeah. So, dw over dx times dm over dx times dx. Yeah. Okay. So, this one is as far as this is concerned. Yeah. So, we got two parts of that. Okay. So, now remaining is this one. So, we write minus 0 to L here also. So, 0 to L and w and px dx equal to 0. Yeah. Or so, here we can expand, yeah, the expand. So, here first here we will have two things here. So, if either this one is nothing but dm over dx is what? So, dm over dx is, okay, remember that dm over dx equal to minus v. Okay. So, where v is shear force and m is bending moment. So, this is the relation that we derived in the last video lecture, and hence from here we can write like this. We will have w, okay. So, w L, okay. So, w L times v L. Yeah. So, but the minus sign here because dm over dx is a minus b. So, w at L multiplied by b v at L minus sign, and then we will have plus plus W at 0 and V at 0, right. Okay. Then we have minus, okay. And then we have another we can do another integration by parts. Okay. So, here dx over dx is actually gets cancelled like this. So, that means we can just write this multiplied by m. So, minus we can write integration by parts. So, we have dw over dx times m L to 0 and then minus then 0 to L. Okay. So, this whole thing integration by parts. So, one you get this dw over dx times m and then we get this minus, and what else we get? We get d square w over dx square times m. So, here we will get the d square w over dx square times m dx, okay, minus 0 to L w p x dx equal to 0. Okay. So, we can expand further and what we get, or okay. So, or minus w at L, v at L plus w at 0, v at 0 minus, first we get dw over dx, dw over dx and then m. Yeah, so that is one thing. So, minus we say dw over dx at x equal to L times m at L plus dw over dx x equal to 0 m at 0, that we get. Okay. Then we have this minus plus. So, we get plus here, okay, plus. So, just write here plus dot. So, we will continue that side. So, basically what is that? So, top. So, we have whatever we have here plus this one. So, 0 to L. So, 0 to L d square w over dx square m dx, d square w over dx square m dx minus plus okay, and so minus plus, and then we have minus here, minus this value. So, minus 0 to L and then w p x dx is equal to 0. Okay. So, we have all these actually, and these ones can be now we can impose, and we know that w when w is given, I mean when u y is given, w will be 0. Yeah. So, we know that. So, that means accordingly we have to choose. So, if L equal to some, let us say x equal to L, u y is given, then this will be 0, hence you will get rid of that. Yeah. So, according we have like 4 types of boundary condition. You can see we have like VL. If VL is given, then we will have, if VL is given at x equal to L, then this will survive. This we will have if shear force is given at x equal to 0, then this term we will have. Yeah, if u is given at x equal to 0, then this term will go away. If like uy is given at x equal to L, then this term will also go away, because this w will be 0. Here also we can do the same thing. If the slope is given as x equal to L, then this term will be 0. If slope is given at x equal to 0, then this term will also be 0. However, if the bending is given at x equal to L, then this will be there. If instead bending at x equal to 0 is given, then this term will also there. So, we have all the boundary condition we can see here, everything is here already here, okay. And here what we have this, and now we can put the value of what we know. We know that m equal to ei d square uy over dx square, and hence we will get the whole picture. What will we will get? So, we can write the everything from here to here, and what is that? We have minus WL times VL plus W0 times V0, okay, then minus dw over dx, x equal to L, x equal to L times m at L plus dw over dx, x equal to 0, m at 0, okay, plus 0 to L d square w dx square times ei d square uy over dx square dx minus 0 to L w x p x dx equal to 0. So, this is the weak form, right. This whole thing is the weak form, right. So, this is the our weak form. Yeah. Remember that this is true for all w, okay, with only constraints. And what is that? That if, for example, I am giving. So, if uy at x equal to 0 is given, then w at 0 equal to 0, if uy at L is given, then w at L equal to 0. If duy, so theta equal to duy over dx at x equal to 0 is given, then what is 0? Then dw over dx, yeah, dw dx at x equal to 0 is equal to 0, yeah. And if basically this is the slope due to w basically. Similarly, if theta equal to duy over dx at x equal to L is given, then accordingly dw over dx x equal to L will be equal to 0. So, this is the conditions, and this is consistent with what we have been doing earlier. So, we can accordingly we can identify which will be 0, which will not be 0. So, basically either this is given or this is given. I mean either ui at L is given or v at L is given. If uy at L is given, then this becomes 0. So, okay, this is exactly what we have been doing in other cases. Okay. So, once we have that, the next thing will be to do the basically do the finite element analysis, meaning that we have to now solve the problem. Okay. So, solve the problem now. Next is solve the problem. Solve the problem using finite element method. Okay. Now, here we are going to use I mean we will use some shape functions, right. So, this one is straightforward and this we are going to use anyway. Yeah. So, this one we can like we will not use this one. Let us not analyze this further, we will just take these ones first. Yeah. Okay. So, because our u and w will have will depend on the shape function. So, we just analyze only this one and at the end we will join them together. Okay. So, this is the boundary condition we will set aside for some time right now. Okay. So, here if we have only this one, we are going to first write u y as a function of shape function, similarly w, and then from there we will go. So, shape function in this case, what kind of shape function are we going to use? Okay. So, shape functions. So, okay. So, this is a beam basically, and here we have x equal to 0 and here we have x equal to L. This is two noded beam element, but it will have two degree of freedom. So, one will be this one. So, here we have u y 1, yeah. Here this is u y 2, and then we have bending moment. So, we have this bending moment here. Yeah. So, no, not bending moment, the angle. Yeah. So, this is theta. Yeah. So, theta 1, let us call it, this is theta 2. Okay. And we know that theta 1 is nothing but duy over dx at x equal to 0 and theta 2 equal to duy over dx at x equal to L. So, this is the difference between theta 1 and theta 2, both are, I mean they are actually the same thing, only but at different places, and this one is u y 1 is nothing but this is u y at x equal to 0 and u y 2 is u y at x equal to L. Okay. Now, we are going to find a shape function such a way that it is going to this, let us write 1 and 2. So, this is going to represent how. So, we have to write, there will be 4 shape functions first of all. 4 shape functions, why? Because there are 4 degree of freedom, that is why. So, 4 shape functions because there are 4 degree of freedoms. Okay. And we will write u. So, we will write u, for example, u x, u y as a function of x as n1, okay, let us say is called n1 and then u okay, n1 u y1, n2 okay, n2 and then this will be u y2, n3 theta 1 plus n4 theta 2. There are 4 shape functions n1, n2, n3, n4 and we write like this one u. Yeah. So, you can see that at x equal to 0, if we have, right. So, we have uy1 which is equal to uy at x equal to 0, which will equal to n10 times uy1 plus n20 uy2 plus n30 theta 1 plus n40 theta 2. What you can see here is basically, since this is equal to this, and hence n10 will be 1, all others will be 0. Yeah. So, that really means n10 equal to 1, n20 equal to 0, and n30 equal to 0, n40 equal to 0. Yeah. Okay. So, this is like this one, but at the same time remember that if we say theta equal to d uy over dx. Yeah. So, that means our theta as a function of x is given by d dn1 over dx times u1 uy1 plus dn2 over dx times uy2 plus dn3 over dx times theta 1 plus dn4 over dx, yeah, times theta 2, right. So, theta is given like this one, sorry, from the same equation, now theta is given like this. Yeah, that really only tells that theta, we know just theta 1 equal to theta 0 will be equal to what? dn1 over dx at x equal to 0 times uy1 plus dn2 over dx x equal to 0 times uy2 plus dn3 over dx, right, at x equal to 0 theta 1 plus dn4 over dx x equal to 0 theta 2, right. Okay. And this, you know, this one is if this is true, theta 1 is equal like this one. So, then what you know, that this has to 1, all others have to 0. So, this only tells us that dn1 over dx at x equal to 0 has to be 0, dn2 over dx at x equal to 0 has to equal to 0, and dn3 over dx x equal to 0 has equal to 1, yeah, from here. So, that we have this equal to this, and also dn4 over dx at x equal to 0 has equal to 0. So, that means we have to find out n1, n2, n3, n4 such that this is one condition it has to satisfy. There is another set of equation also, constant also it has to satisfy like this one. Yeah. So, this is what we have to find out in that case, what is the value of n1, n2, n3 and n4. And similar analysis we can do for the other point, means x equal to L, right. When x equal to L, then we, you know that n1 at x equal to L has to be equal to 0, n2 at x equal to L has to equal to 1, and at L it has to be 0, L equal to 0. And similarly here also, when we do the derivative of this one, yeah, and if we have put L here, then theta 2 becomes theta L, and all here value becomes x equal to L, x equal to L, L and L, and hence we will see that this value at x equal to L will be equal to 1, all others derivative has to be equal to 0. So, basically we can actually sum up here with the requirement of n1. What will be the requirement of n1, for example? Okay. So, n1 will be something like this. So, this is say this is a beam, and so the n1 value will be equal to 1 at this value, and slope will be 0, meaning that dn over dx is 0, right. So, this is, see here, dn 1 over dx equal dn1 over dx equal to 0, right. So, this is 0. So, that means this is n1 is equal to 1 at x equal to 0, and slope, but slope is 0, and similarly this will be 0, the value will be 0 here, and slope will also be 0. That is coming from the second requirement. Yeah. Okay. So, basically n1 will be something like this. So, this will be go like 0, and here also it will be equal to 0, like this one. This is how n1 will look like. Yeah. So, we have to find out what kind of function this one. Yeah. So, this is n1 0 equal to 0, and dn1 over dx x equal to 0, sorry, this will be equal to 1, n1 equal to 1 equal to 0. Here n1 at L is 0, and dn1 over dx at x equal to L is also equal to 0. So, this coming from this requirement, yeah, these two requirement, and this one coming from, if you do the similar analysis for x equal to L. Yeah. So, basically the we have this is given as this one. So, when x equal to L, and then if you we will automatically okay. So, let us do it. Okay. So, instead of, okay, so at x equal to L, how we got this one? So, we can explain here. Okay. So, we know that u y is equal to n1. So, u y at L will be equal to n1 L. Yeah. So, times u y is n1 L times u y1 plus n2 L times u y2 plus n3 L, then theta 1 plus n4 L theta 2, but this is equal to u y at this, we call it y u2. So, this is the whole thing is equal to this one, means this one. So, that only this will be 1. So, that really means, that tells you that n1 L is 0, right. So, n2 L is equal to 1, n3 L is 0, and n4 L is also equal to 0. Yeah. So, n1 L equal to 0, this is what we are writing here. Similarly, theta, you can write theta 2, which is equal to dy duy over dx at x equal to L will be equal to, so we will take derivative. So, dn1 over dx x equal to L uy1 plus dn2 over dx x equal to L uy2 plus dn3 over dx x equal to L theta 1 plus dn4 over dx x equal to L times theta 2, which is equal to theta 2 only, right. So, this is theta 2 only. So, what we will get? That means this will be equal to 1, all others will be 0 only. Yeah. So, this implies that dn1 over dx x equal to L, yeah, is equal to dn2 over dx, x equal to L is equal to dn3 over dx, x equal to L is equal to 0 simply, yeah, and we have dn4 over dx, x equal to L is equal to 1, yeah. So dn1 over dx at x equal to L is 0, yeah. So same thing we are writing it here. So we got these conditions, and if you see that, what it tells you that this curve has to be value 1 here, and the slope has to be 0, and here the value is 0 and slope is also 0. So this will look like something like this one. Only thing is, now we have to find out what kind of function this one is. Now looking at it, if since this is 0, right, so this value is 0 and the slope is also 0, that means it has the double root here, yeah. So that is tells you this is a double root here, double root at x equal to L. So that means, that tells you that x minus L square term will be there, yes, because so that even if you take derivative of that, x minus L will be there, yeah. So that means double root. So that means n1 will have a factor of x minus L square, rest is this one, yeah. Now we also get here we will have value which is equal to dn1 over dx equal to 0, yeah. So that means here there will be some one more thing here that will make this also equal to 0, means derivative not only as x equal to L, but x equal to 0 also as 0. Okay. So that we have to find out what will be the value of n1. Now if we can guess the form of n1, then it will be easier to derive the n1, right. So looking at this one, we have like 4 constants here, right. So that really means that if the n1 has 4 unknowns to be determined, right. So since we have the 4 equations here, that really means there has to be 4 terms in n1, that really means n1 will be of this type. So n1 will be alpha plus beta x plus gamma x square plus delta x cube. So this is a cubic, basically cubic function, yeah. So the n1 has to be cubic because of the we have 4 constants. So in order to find out the value of this coefficient, we need the 4 equations, and those 4 equations are given by like this one. So we can directly put these values here, and we can find out the value of alpha, beta, gamma, delta. This is one way of doing it. The other way is just looking at the function. We are going to first see this is double root here, so x minus L has to be there, x minus L square. Rest is here, what is that? We have to now find out, okay. And we know that since this is cubic, so this they will be multiplied by x plus a, let us say, right, and so we can only guess that n1 x equal to, let us call it a, and then x plus b multiplied by x minus L square. This is of this form, yeah. So x minus L square is there because of this double root, and this one to make this cubic, and then we have 1 here to scale it, okay. Now given that, now we can put the values and see whether it works or not. So at x equal to L, this will work, this because, and even if we take a derivative of this will work. Only at x equal to 0 we have to see. So we know n1 at 0 has to be equal to 1. So this will be a times b times minus L square So, becomes AB L square. Yeah. So, this we get, or simply we get AB is equal to 1 over L square. Second thing is dn1 over dx we can do, and what we find? We find a x minus L square plus a x plus b multiplied by 2 x minus L, right. So, dn1 dx x equal to 0 has to be equal to 0. So, is here we have a minus L square plus a times b times 2 minus L. Yeah. So, is equal to, we get a L square, right, a L square plus rather minus 2 a b L, right, is equal to 0, or simply from here we will get something out of it, or so this L and this L cancels out, and we get a and a will cancels out. So, what we get, this L 2 cancels out, then a here and a here cancels out, and we get L is equal to, or L minus 2b equal to 0. Yeah. Or we get b equal to L over 2. Yeah. So, b equal to L over 2, that we get. So, L over 2 we write here, and then a, and that tells us a basically a equal to 1 over L square divided by 1 over b multiplied by 1 over b. So, 1 over, right, a equal to this multiplied by 1 over b. So, 1 over b is 2 over L, so multiplied by 2 over L. So, this becomes 2 over L cube. So, that means b will be 2 over L cube, this will be L over 2. So, we get n1 value. So, n1 x will be 2 over L cube, then x plus L over 2, and then x minus L square. So, we get n1 x. Similarly, for second one, for n2, similarly we can do the analysis. For n2 we see this kind, right. So, we have how it goes, this is just opposite basically, right. So, this will be n2 will be 1 here, and this will go like this. Yeah. So, we have 1 here, the slope is 0 here, value is 1, this is 0, slope is 0, and this also. So, here this will be just the mirror image of that. So, n2 x, yeah. So, will be equal to, it should have of this form only, and what we know that it will have a double root here. So, it will have x squared term here, right. So, we will have x squared term. So, we can do the similar analysis, and in this case what we will do? We will do this equal to, write a times x plus b and then x square like this one. Yeah. Okay. So, that these are double here. So, this automatically satisfied here. So, only thing here. So, we say n to L is equal to 1 is equal to a L plus b L square, right. So, you get the one equation here, and also dn2 over dx is equal to a x square plus a x plus b times 2x. So dn2 over dx at x equal to L is equal to a L square plus 2a L plus b times L has to be equal to 0. Yeah. Okay. So what we get? We get is equal to or we can say or we have a common, so we can get rid of a will be cancelled. Yeah. Okay. So okay, so we will get rid of a, and then after that what we have is L square. So or L square plus 2 L plus b L equal to 0. Okay, another L we can get rid of, so we have L plus 2 L plus b equal to 0. Yeah, we can simplify further, so we will get L plus 2L plus 2b, so 3L plus 2b equal to 0. So 3L plus 2b equal to 0. Yeah, so 3L plus 2b equal to 0, and or we will get b equal to minus 3 over 2L, minus 3L over 2. Okay, and hence a we will get as, so from here we can find out a, from here a, so a will be equal to 1 over L plus b L square. So a equal to 1 over a, sorry, a equal to 1 over L plus b L square. So L plus b L square is equal to, so this tells us that L plus b is equal to L minus 3 by 2 L equal to minus L over 2, right. So this will equal to 1 over minus L over 2 multiplied by L square, so minus 2 over L cube. Yeah, so this is what a is. So that makes, so b we get minus L over 2, a we get minus 2 over L square, and hence we can find out n2 as a function of x will be a minus 2 over L cube, then x plus b, so we get x minus L over 2, and then we have x square. So we get n2 like this. I realize there is a error here. So this is b is equal to minus 3 over 2L. So this x plus b, so this will be 3. So this, okay. So x minus 3 L over 2 like this one. So that when we have x equal to 0, we have 0. When x equal to L, then we should 1. So we have L, if you put L here, so we get minus L over 2 multiplied by L over L square. So we get minus L cube over 2, and hence total will be equal to 1. So good. Okay, now the third thing, the n3, and n3 is about the slope basically. So what he says? He says the slope is unity. Yeah, and here it will be equal to 0. Yeah, so this n3 has slope which is equal to 1. Slope is 1. However, the value is equal to 0. Value is 0 here, and slope is also 0 here. Yeah, so looking at this one, you know that slope is also 0 here. Hence it will have double root here, double root at x equal to L simply, and here it will have a single root. Yeah, so single root here, single root here. Hence n3x may be simply given by equal to a multiplied by x, simply x, because we have x here single root, and here it will be double root, and hence this will be x minus L square. Yeah, okay. So all the four things like all these things will be automatically satisfied. Only thing is the value of slope is unit. Yeah, so dn, so we can find out dn3 over dx equal to, so let's do here. Okay, so dn3 over dx will be equal to a x minus L square plus a x multiplied by 2x minus L. Yeah, and if you put x equal to 0, then what we get? So that means dn3 over dx x equal to 0 is equal to, put 0 here, so minus, we get a L square, a L square plus here we put 0, so everything will be 0 in this case, so we get simply a L square, which is equal to 1. So hence a equal to 1 over L square, and hence n3 will be 1 over L square. So n3x, yeah, n3x will be 1 over L square, and then you have x, x minus L square. Okay, so we got n3. Now n4x, it is also the same thing. So what we are going to get is the slope is 0, value is 0 here, and slope is 1 and value is 1 at the other end. So here slope is 0 and the value is 0, here slope is not, the slope is 1 and value is equal to 0. Yeah, so this is x equal to 0, x equal to L here, and how can you find out? So here it will have double root here, so we can say this is equal to a x square, and there is a single root here, so we have x minus L. So like this one. Again we can put, we can take the derivative, dn4 over dx equal to 2ax x minus L plus ax square. Yeah, so dn4 dx at x equal to L will be 2al, so will be equal to, so if you put x equal to L here, this term will be 0, only this term we have, so we get a times x equal to L, so again a L square only, right? So a x equal to L, so a L square. Yeah, so the, and which is equal to 1, so that tells us a equal to 1 over L square, so which is similar to the earlier case. So in this case also we get a equal to 1 over L square. So that means we get n for x is equal to 1 over L square x minus L. Yeah, so we got all the 4 shape functions. Yeah, and the next thing is to use all of them. So n4 is equal to 1 over L square x square, like this one. Okay, n3 we got from here, which is 1 over L square x x minus L square. Then we have n2x. Okay, so n2 we got here, so minus 2 over L cube, and x minus 3 over 2 x square. So minus 2, so minus 2 over L cube, minus 2 over L cube, then x minus 3 over 2, x minus 3 L over 2, x minus 3 L over 2, x minus 3 L over 2, and then x square. So x square here, then n1x is also equal to, okay, this is a minus here, remember, equal to 2 over L cube, and x, then we have x, yeah, here x plus L over 2, so x plus L over 2, x plus L over 2, and then we have x minus L square. Yeah, so we have all these shape function n1, n2, n3 and n4. Now we can use these to derive the stiffness matrix.